A large block system can hide a smaller system inside it. The Schur complement is exactly what remains after one block is eliminated. Start with this block matrix equation. It represents two coupled vector equations for the unknown blocks x and y. We assume A is square and invertible. That single assumption lets us solve the first block equation for x. The first block row is ax plus by equals p. Move by to the other side. Now ax equals p minus by. Multiply by A inverse. The first equation now gives x entirely in terms of y. The second block row is cx plus dy equals q. Substitute the expression from the first row. The variable x is now gone. Distribute CA inverse without changing the order of any matrix factors. Move CA inverse p to the right, leaving both y terms on the left. Factor y on the right. Its new coefficient is d minus CA inverse b. We name that coefficient S. It is the Schur complement of A in the original block matrix. The entire coupled problem has been reduced to this smaller system for y. Once y is known, return to the first row and recover x by back substitution. So the Schur complement is simply block Gaussian elimination written as a reusable formula. To understand the correction term, follow one change in y around the coupled system. The matrix B sends a change in y into the first equation. A inverse converts that disturbance into the corresponding response of x. Then C sends the response of x back into the second equation. The effective coefficient is the direct effect d minus the feedback already explained through x. Now use the smallest possible example, two scalar equations with the same block structure. The first equation gives x equals 7 minus y divided by 2. Here the inverse of A is simply 1/2. The Schur complement is 5 minus 3 times 1/2 times 1, which equals 7/2. The reduced right side is 19 minus 3 times 1/2 times 7, which equals 17/2. Solving the reduced equation gives y equals 17/7. Back substitution gives x equals 16/7. The first equation checks 32/7 plus 17/7 equals 7. The second equation also checks 48/7 plus 85/7 equals 19. The same elimination gives a useful determinant identity. The full determinant equals determinant A times determinant S. A unit lower triangular elimination matrix turns the full matrix into block upper triangular form without changing its determinant. When A is invertible, the full block matrix is singular exactly when its Schur complement is singular. Remember the pattern. Solve one block, subtract its feedback, solve the reduced block, then recover what was eliminated. That is the Schur complement, not an isolated trick, but the exact coefficient left after block Gaussian elimination.